Hello and welcome to this revision session on thermal physics, which is part of the AQA A-level physics qualification. So in today's revision session we're going to look at answering examination questions for thermal physics. So if we've been successful and we've learned in this revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and then understand what topics we need to improve upon for A-level physics. So how can we prepare in this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. Now when you're doing this, make sure you write out your answers in full sentences and show your working out. Whilst on the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, what are the tips on how to revise for A-level physics? So first step is to learn the key facts. So use your revision guides, class workbooks, prep notes and textbooks to learn the key ideas of the course. Now you might wish to write out notes yourself or make mind maps. Second step is to test yourself. So use things like Caboodle, Seneca, the student knowledge checker to quickly test your own knowledge, and you may wish to do this from your own cue cards. And then the third step is practicing examination style questions. So using exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. And you may wish to download your own exam past papers to do this. So the three steps of learning the key facts, then testing yourself, and then practicing exam style questions are the way forward for revising A-level physics. So let's start off by practicing a few multiple choice questions. So in this first question, at absolute zero an ideal gas will do what? So pause the video now, then unpause the video when you want to go through your answer. Right, so we've got to understand what absolute zero is. Now at absolute zero, a gas has no kinetic energy because the gas particles have stopped moving. It only has potential energy. So the gas particles do not move and will collide with the container they're in. So as such, they won't have any pressure because pressure is caused by the collisions of the gas particles with the container that they're in. So our answer is B. Next question. A student plans an experiment to test Charles' law for a gas. Which quantity of the gas must be measured and which must be kept constant? So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one we've got to consider what Charles' law is. And Charles' law is the law linking the volume and the temperature. As such, they must be measured whilst the pressure and the mass are variables which we need to control to gain valid results because they can affect the values of a gas. So therefore our answer is C. Next question, which process will increase the kinetic energies of the particles involved? So pause the video now, then unpause the video when you want to go through your answer. Now it's important to note that what will happen here. So the answer is going to be B, because if you think about it, boiling and melting, options A and D are going to change the potential energy because you're changing the state. So we've got two options here, compressing the gas or expanding the gas. Now when you compress the gas, you are putting work into the gas to compress it, so therefore the overall internal energy of the gas must be increasing. So because we're not changing the state, we're just compressing the gas, it must be the kinetic energy store of the gas that's changing, so therefore it's going up. So our answer is B. The next question, when an ideal gas at temperature of 27 degrees Celsius is suddenly compressed to 1/4 of its volume and the pressure is increased by a factor of 7, what's the new temperature of the gas? So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing we've got to be aware of is what's our equation for an ideal gas. So we know that PV is equal to nRT. Now we know that the pressure is increased by a factor of 7 and the volumes decrease by a factor of a fourth, so it's gone down to 1/4. So overall PV has changed by 1.75, 7 times by 1/4. Now as N and R are constant, if the left hand side has gone up by 1.75, the right hand side has gone up by 1.75, but N and R are constant, so only T can change by 1.75 to go up in that direct proportion as the equation suggests. Now it's important to note that this equation PV equals nRT is for when T is in Kelvin, not degrees Celsius. So you've got to convert 27 degrees Celsius into 300 Kelvin, and then we multiply that by 1.75, which is 525 Kelvin, and then turn that back into degrees Celsius by minus 273 from that. So our answer is 252 degrees Celsius, which is the answer of D. The next question. Which statement is true about an experiment where Brownian motion is demonstrated using smoke particles in air? So pause the video now, then unpause the video when you want to go through your answer. Right, so again, we've got to understand what Brownian motion is showing us and what the effect is demonstrating. Now the answer is C, because Brownian motion indicated that gases were made out of air particles, and the air particles moved in a random motion. Now this was indicated as the air particles collided with the smoke particles and therefore caused the smoke particles to move randomly because they're being hit randomly by the air particles. And we could observe the smoke particles moving randomly and then work out that air particles existed. So the answer was C. Let's have a look now at a few longer questions in thermal physics. So the first question is that nitrogen is heated from 70 Kelvin and is completely turned into a gas after 890 seconds. Calculate the specific heat capacity of liquid nitrogen and give an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do we answer this particular question? So we've got to understand how much energy is being completely supplied to the nitrogen. So we've got to understand that the total energy supplied is going to be 12 times by 890. So therefore, we can know that it's 10,680 joules being supplied to change this. But we also know that the latent heat of vaporization for nitrogen is therefore going to be 2 times 10 to the 5. So we then work out the energy needed to evaporate it at its boiling point, which is going to be 0.05, because that's how much mass in kilograms you have of nitrogen, times by 2 times 10 to the 5. So therefore we can subtract that from our value. So therefore we can say that E is equal to MC triangle T. So therefore C is equal to E over M triangle T. The energy is going to be the total energy minus the energy needed to change the state. Then we divide that by the mass times by our change in temperature. So we get 1.9 times 10 to the 3. Now what's the units of specific heat capacity? It's joules per kilogram degrees Celsius or joules per kilogram Kelvin, which is an important idea. Now, let's have a look at our next question. So the work done by the nitrogen in the cylinder when expanding due to a change of state is X. The energy required to change the state of nitrogen from a liquid to a gas is Y. So deduce which is going to be greater, X or Y. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to use this idea of volume is going to be mass over density, and you can see the density of liquid nitrogen and the density of nitrogen gas. So what you would do is, we know that the nitrogen for each of them has a mass of 0.050. Actually, it doesn't make a difference which one, what mass you use, because we see it's the same value for each one, will cancel through. So you work out how much nitrogen gas you'll need in volume, then you work out how much nitrogen liquid you would need in volume. Now at that point the work done is therefore going to be P times by the change in volume. So therefore we'll note that the pressure, which we knew before was 1 times 10 to the 5 multiplied by the work done. So you can work out that it's going to be larger for the liquid, because it's going to be a greater change in volume. Right, next question. State what is meant by the internal energy of a gas, and an absolute zero of temperature can be interpreted in terms of the ideal gas laws, or the kinetic energy of particles in an ideal gas. Describe these two interpretations of absolute zero of temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to just learn these definitions. So what's the internal energy of a gas? It's the sum or the total of all the energy stores in a particle or atom or molecule. So you've got both the kinetic energy store and the kinetic and the potential energy store. Now because it is a gas, you would say that obviously you've got to say the kinetic energy of the gas itself. Now the second one is the interpretation of absolute zero. So it's important that you understand that it is in the gas laws, it's the temperature in which the volume or pressure of a gas extrapolates to zero. So you would note that it's the point for a gas in the gas laws that when it does not exert pressure anymore. So you could say that when PV equals nRT, it's the temperature where PV or V or P is zero because it'll link through, or when you plot a graph of volume against temperature, it's where it crosses the temperature axis, okay, where the volume will equal zero. Now the second interpretation is the particle interpretation of this, and that's using the idea that the kinetic energy is the temperature, it links to the temperature, so therefore it's going to be when the kinetic energy of the particles is zero, because at absolute zero the particles stop moving. Let's have a look at our next question. A mixture of argon atoms and helium atoms in a cylinder is enclosed with a piston. The mixture is at a temperature of 310 Kelvin. Calculate the root mean square speed of the argon atoms in the mixture, then compare the mean kinetic energy of the argon atoms and the helium atoms in the mixture. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do we answer this first particular question? Well, the first thing we've got to note is we're given the molar mass of the argon. So what we can therefore do is we can therefore work out the mass of one argon atom. So to work out the mass of one argon atom, we would do the molar mass, which we're given, divided by Na, which is Avogadro's constant, which is 6.023 times 10 to 23. So therefore, the first thing we do is we work out that the mass of one argon atom is 6.6 times 10 to the minus 26 kilograms. We can then work out the root mean squared speed by using our equation, a half mc squared equals 3 over 2 kt. We can then rearrange it to work out what CRMS is. So CRMS is 3 kt over m to the power of a half, or square root, it's the same thing. So we pop our values in. Now 3 obviously is just a number, K is a constant found in the equation book, T is the temperature in Kelvin, which we know from the question is 310. We can then divide that by the mass of one atom. Now remember, because a half mc squared links into the mass of the atom, not the overall substance, and then we square root and get 440 meters per second. Now the next question is comparing the values. Now the important thing to note is, okay, that it says in the question that the argon atoms and the helium atoms are enclosed in the cylinder and the mixture has a temperature of 310 Kelvin. So that's important to note that because they've both got the same temperature, both gases will have the same or mean average kinetic energy. Now they might not be moving at the same speed because it's a half mc squared, so therefore if one mass is higher, the value of c squared is going to be lower, but they will have the same kinetic energy if they're at the same temperature. Now the next question says, explain in terms of the kinetic theory model why a pressure is exerted by a gas on the piston. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to be aware of how pressure works in the kinetic theory model. So particles or molecules or atoms will collide with the container, the piston, the wall, and there'll be a change in momentum. Now how do you know there's a change in momentum? It's because there's change in direction. So there will always be a change in momentum. Now we've got to understand that force is the rate of change of momentum. That's Newton's second law of motion. So we can therefore say that we're going to have a force on the piston because the momentum of the gas particles has changed. So therefore we can say pressure is force divided by area, so therefore we can know that there's a force there, there's an area of the piston, so you can work out our pressure. Next question. The mixture of gases in the cylinder stays the same. Explain, using the kinetic theory model, two changes that can be made independently to reduce the pressure exerted by the gas. So pause the video now, then unpause the video when you want to go through your answer. Right. So how can you reduce the pressure exerted by the gas? So the first way you can do this, if you think of the kinetic theory model, that pressure is caused by the collision of the gas particles with the container, is you can increase the volume. Because if you increase the volume, it will increase the time between collisions, between the gas particles hitting the side of the container, or you could say that there's less frequent collisions. So therefore, you could argue that therefore the pressure is going to go down, or you could say that it'll increase the area of the piston in the wall, so therefore even if the force stays the same, the area gets bigger, so the pressure goes down. The second way in which you can reduce your pressure is by decreasing the temperature, because if you decrease the temperature, you're decreasing the speed at which the particles are moving at, because temperature links with average kinetic energy of the particles, so therefore there'll be a reduction in momentum, so therefore a reduction in the change of momentum, because if the values go from plus to minus and it's a smaller number, you're going to have a smaller change, so therefore our pressure produced is going to be smaller. Or you could also say, quite rightly, that if the temperature goes down, well then the particles are travelling slower, so there's less frequent collisions as well. So both ways will reduce the pressure exerted by the gas. Next question. A perfectly insulated flask contains a sample of metal M at temperature minus 10 degrees Celsius. Figure 1 shows how the temperature of the sample changes when the energy is transferred to it at a constant rate of 35 watts. Firstly, explain how the energy transferred to the sample changes the arrangement of the atoms during the time interval TA to TB, and then state what happens to the potential energy of the atoms and to the kinetic energy of the atoms during the time interval A to B. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to note that in time A to B, we're going to be changing the state. Now, it's important to note this because you can tell that the temperature itself is not changing, so any energy is going into changing the state. So therefore, the energy is transferred to though the atoms move the center of their vibration or they break some of their atomic bonds. So therefore, if you look from here, from A to B, the atoms are moving further apart. So what's happened to the potential energy and the kinetic energy? Well, it's important to note that the kinetic energy remains constant. So it's important to note this because if we note on this idea, okay, that the kinetic energy is constant because the temperature, which is a representation of kinetic energy, stays the same. But the potential energy increases. How do we know that? Because it's a flat line, so there must be a change in state. And because we're heating it up, we're putting temperature into it, we're putting energy into it, so therefore the potential energy increases. The next question says, the sample has a mass of 0.25 kilograms. Determine the specific heat capacity of M when in the liquid state, and then state an appropriate SI unit for your answer. Now, to help with this one, you might want to go back and just look at the graph again here, okay, to see if you can get some values from the graph, which will help you derive the specific heat capacity. Right, so pause the video now, then unpause the video when you want to go through your answer. Right, so it's important to note that we know that the equation for heat capacity is E is equal to MC triangle T, or else MC delta theta. Either way, it's fine. Now, to work out our energy or our change in energy, it's going to be power times by time. So what do we know? We know that the power from the previous question we looked at, it says that we've got a constant rate of 35 watts. Okay, so we know that we've got 35 watts there. We can see on the graph how long it takes to change when it's in its liquid state, so we can work out the time there. Now note we work in seconds, so you've got to change it into seconds here. Then we divide it by the mass, which is given in the question with 0.25, multiplied by the change in temperature. Once again, this change in temperature is given on the graph. So we're starting at, if we have a look on here, we're starting at 28 degrees and we're going to, I believe, 112, so you can work it through like that, and you've got your time, but obviously converted into seconds as well. So therefore you can work it through to get 370. Now again, what's the specific heat capacity? It's joules per Kelvin degrees Celsius, or joules per Kelvin, so kilogram Kelvin. So it's just joules per kilogram Kelvin, or joules per kilogram degrees Celsius. Sorry about that. The next question says, Table 1 shows the specific latent heats of fusion L for elements that are liquid at similar temperatures to M. M is known to be one of the elements in Table 1. Identify M. So remember again, what do we know? We've got our graph before, so if we look back on our graph to help us work these things through. So pause the video now, and then unpause the video when you want to go through your answer. Right, so how would you do this? So we'd say L is going to be equal to the power, so the power times by the time over M. Why is that? Because we know E is equal to ML, and E is the power times by the time. Okay, and then we know what our mass is. So what we need to do is we know our mass is 0.25 kilograms. We know that our power was 35 watts because it told us previously in the question. We can go back on the graph and we can determine the time in which it changed state, because latent heat refers to changing of state. So we know that it started changing state at, let's get this right, 1.8 minutes, and then changed at finished changing state at 11.2 minutes. So what we can therefore do is we can then look at that, we say 11.2 minus 1.8, but then we convert that into seconds, and we then times that by 35 to get our energy, divide by our mass is 0.25, so we get 79 kilojoules per kilogram. Now it's important to know that what's that close to? It's going to be gallium. And why is it slightly different? Well, there's going to be inaccuracies in the investigation, so it's not going to be exactly 80. Let's have a look at our next question. Helium gas particles are single atoms that behave as an ideal gas. A container of helium gas is used to inflate an empty balloon. Immediately after inflation, the gas in the balloon has a pressure of 106 kilopascals, a temperature of 288 Kelvin, a volume of 1.4 times 10 to the minus 2 meters cubed. So show that firstly the number of atoms in the balloon is approximately 3.7 times 10 to the 23, then that each helium atom has a mass of 6.6 times 10 to the minus 27 kilograms. So calculate the density of the gas in the balloon. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do we work this one out? Well, we can look in the back of our equation book and we know that we've got an equation which has number of atoms in it, and that is PV is equal to NKT, where big N is equal to the number of particles in the substance. So we can then rearrange it and make N the subject. So we can say N is equal to PV over KT. We've got P, we've got V, we've got K because it's a constant, and we've got T. Now the only thing we've got to remember is it's 106 kilopascals, so we've got to change that kilo into just a normal value, so it's 106 times 10 to the 3. So we can put those all in and we get 3.73 times 10 to the 23. Now again, why do we give it to 3 sig fig? Because all the values given in the question are given to 3 significant figures. Now our next question is asking for the density of the gas in the balloon. Now what we need to do is we need to work out the total mass of the atoms in the balloon. So we know that there are 3.73 times 10 to the 23 atoms in the balloon. We know the mass of each atom is 6.6 times 10 to the minus 27. So we can therefore work out our total mass by doing that. We can then say density is mass divided by volume. Again, that equation is given to you in the back of your equation book. We know our volume because it's given in the start of the question, so we can work it out to be 0.18 kilograms per meter cubed. Next question. The rate of flow of water through a panel is 45 grams per second. The water enters the panel at a temperature of 15 degrees Celsius and absorbs energy from the panel at a rate of 1.7 kilowatts. Calculate the temperature of the water as it leaves the panel. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this question? Well, again, you talk about heating something up. So we'll use our equation E is equal to MC delta theta, or E equals MC triangle T. Now we know that we want to make the change, we want to work out the change in temperature. So we'd say that E is going to be equal to MC triangle T, so therefore triangle T or delta theta is equal to E over MC. We've got C, 4,200. We've got M. Now again, we'll take it over 1 second. So 45 grams per second becomes 45 grams. So we turn that into kilograms. We then know that 1.7 kilowatts in 1 second becomes 1.7 kilojoules, because a watt is 1 joule per second. So therefore we can say it's 1,700 divided by 0.045 times by 4,200. So therefore we get our value of our delta theta. Then we can add that onto our starting temperature to work out the temperature at the end to get it to be 24 degrees Celsius. Next question. The equation PV equals a third NM C RMS squared applies to an ideal gas. The derivation of the equation depends on the assumptions made about the gas. State 2 of these assumptions. Then a sample of an ideal gas has a temperature of 12.5 degrees Celsius. The mass of each particle of this gas is 6.6 times 10 to the minus 26 kilograms. Calculate the root mean squared speed for the particles in the gas, given your answer to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important you know all the assumptions about an ideal gas. So the major ones regarding the gas itself are as follows. There's negligible forces between the particles. The volume of the particles is negligible compared to the volume of the container, so they're point masses. The particles collide elastically, and the collision duration is negligible. It doesn't exist compared to the time between the collisions. Like I said before, it's very important you just learn the assumptions of the ideal gases. Now the next one is we need to work out the CRMS. So what I would do is I'd look in the back of my equation book and I'll see I've got an equation which says a half mc squared is equal to 3 over 2 kT. Now from the information we've been given in the question, we've got m, because that's the half mc RMS squared. M is the mass of one particle, so we can use that mass in our equation. We've got a temperature for 3 over 2 kT. Now again, K is a constant, so it's just a value. Now T has to be in Kelvin, so we change 12.5 degrees Celsius into Kelvin. We then pop the numbers into the equation, rearrange for CRMS, and we get our answer out to be 423 meters per second. Now again, how many sig figs should you give it to? So you should give it to 2 significant figures, because 6.6 times 10 to the minus 26 is one of the values given, and that's 2 sig fig. You might say, well, what about 12.5? Because that's 3 sig fig. Well, you always go with the lowest number of sig figs given in the values of a question. So 2 is smaller than 3, so you go with 2. Next question. A gas has a density of 12 kilograms per meter cubed when its temperature is 860 Kelvin and its pressure is 2.1 times 10 to the 7 pascals. Show that 60 kilograms of a gas contains approximately 9 times 10 to the 27 particles. Calculate the molar mass of the gas and then state an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we need to look at, we've got density and we've got pressure, so we then need to think about our volume. So we can say that density is mass over volume, so therefore we can use that to then work out our volume by doing volume is mass over density. So we've got our mass is 60 kilograms, we've got our density is 12 kilograms per meter cubed, so therefore, there's our density, so therefore we can work out the volume. We can then say PV is then equal to nRT, or I would actually do PV equals big N KT, where N is the number of particles. We then make a big N the subject. We say big N is equal to PV over KT. We've got T at 860 Kelvin. We've just worked out what V is. We've been given P in the question, 2.1 times 10 to the 7 pascals. K is a constant, so therefore we can work out big N to be 8.8 times 10 to the 27. Then calculate the molar mass. Well, we know that the molar mass, we know that we can have the molar mass is because we're going to say that the mass is going to be equal to the number of moles times by the Avogadro constant. So what you can therefore do is therefore you can say that M over N will give you your molar mass, so therefore we can work it through like that to get 4 grams per mole. Next question. The gas is heated at a rate of 75 megawatts as it flows through a pipe. A mass of 60 kilograms of gas flows through the pipe each second. The gas enters the pipe at a temperature of 860 Kelvin. Calculate the temperature of the gas as it leaves the pipe. So pause the video now, then unpause the video when you want to go through your answer. Right, again, we've got to use our equation that E equals MC triangle T, or E equals MC delta theta. So what we can therefore say is we can say that if we take it over 1 second, we can turn our 75 megawatts into 75 megajoules, and we've got our mass to be 60 kilograms, because this is a 60 kilograms every second, so take it per second. So therefore we can say that 75 times by 10 to the 6 equals our 60, our mass, times by our heat capacity, which is 4.9 times 10 to the 3, times by our change in temperature. We can therefore work out what our change in temperature is. We can then add that to the starting temperature, which is 860, to get our temperature at the end, which is going to be about 1100 Kelvin. Then here's our next question. The temperature of the helium in the balloon changes from 25 degrees to minus 50 degrees during the balloon's ascent. Calculate the change in internal energy of the helium. 1 mole of helium has a mass of 4 grams. So pause the video now, then unpause the video when you want to go through the answer. Right, so how can you work this through? Well, firstly, what do we know? We've been given in this question the change in temperature. Now we know the change in temperature is 75 degrees Celsius because it's gone from 25 degrees Celsius to minus 50 degrees Celsius. So the change is 75 degrees Celsius or Kelvin because they're interchangeable at this point. How many moles do we have? Well, we know that we've got 1 mole of helium is 4 grams, and we know from our previous question that we've got 60 kilograms. So we can therefore work out we've got 145 moles of the helium. Therefore, we can use our equation 3 over 2 nRT to work out our value, because we've got T to be 75, we've got R, which is a constant, and we've got N to be 145 moles. So you can pop those all in and we get 1.35 times 10 to the 5 joules. And this is a minus value because the number's gone down, it's cooling down. Our next question says that for this balloon, the same balloon expands as it ascends. The temperature inside the balloon is always greater than the temperature outside the balloon. Explain by using the first law of thermodynamics how the internal energy of the helium changes during the ascent. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to be aware of how we can use the first law of thermodynamics. Now, the important thing to note is the helium does work in expanding. So when the actual gas expands, because it says it's expanding, heat is being transferred from the balloon to the surroundings because the balloon's at the higher temperature. So it's important to note that both Q and W are negative, so the internal energy falls. So why is delta Q a negative? Well, energy is being lost to the surroundings because the energy will always flow. The kinetic energy of the gas will always flow from the high temperature to the low temperature. So the higher temperature is inside the balloon. It's the gas inside the balloon. So that's losing the kinetic energy to the outside because the outside is the lower temperature. And also, in addition to that, the potential energy is going down as well, because what's happening is that as it's expanding, work is being lost out to the surroundings, because when you compress a gas, work is done into the gas, while when a gas expands, work is done out of the gas to the surroundings. So you're losing energy both from the temperature and from the fact it's expanding, so therefore the internal energy of the gas is going down. So I hope you've enjoyed this particular revision session. So if we've been successful and we've learned in this revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and then understand what topics we need to improve upon for A-level physics. So I hope you've enjoyed this revision session on thermal physics, which is part of the AQA A-level physics course. Thank you very much for listening and watching. Have a lovely day.